Nobel Laureate Chair in Hydrocarbon Chemistry at the local Hydrocarbon Research Institute. He also served as the chairman of the chemistry department at USC. His research encompasses superacid, hydrocarbon, synthetic or organic, organosilicon, and organofluorine chemistry, with particular emphasis in the areas of energy, greenhouse gas abatement, and recycle. He co-invented the direct oxidation methanol fuel cell. He has trained more than 130 doctoral and postdoctoral scholars. He is a prolific author with more than 815 peer-reviewed publications holding more than 100 patents. He has published 14 books. He has received many awards and recognition, including the American Chemical Society Awards, the 2004 Creative Work in Fluorine Chemistry, the 2006 Georgia A. Oler Award in Hydrocarbon or Petroleum Chemistry, the 2006 Richard C. Tolman Award from the Southern California section of the ACS, and the 2018 Late Career Cope Scholar Award. He has also received the 2007 Distinguished Alumni Award from his alma mater IIT Madras and the 2010 CRSI Medal from the Chemical Research Society of India. He has co-shared with the late Professor Oler the inaugural 1 million, the 2013 Eric and Sheila Sampson Prime Minister Prize for Innovation in Alternative Fuels for Transportation by the State of Israel. In 2015, he won the Henry Morrison International Prize of Excellence in Fluorine Chemistry. He is a fellow of the AAAS, a member of the European Academy of Arts, Science, and Humanities, a fellow of European Academy of Sciences, Fluorine Fellow of National Academy of Science, India, and a fellow of the American Chemical Society. He also sits in the editorial boards of several international journals. Professor Prakash book co-authored with G.A. Oler and A. Gilbert, Beyond Oil and Gas, the Methanol Economy, published with Wiley VCH 2006, and it's the second edition 2009 and third expanded edition in 2018. That has been translated into many languages, including Chinese, Hungarian, Japanese, Swedish, and Russian. Is getting worldwide attention. It's such a great honor and pleasure for us to have Professor Prakash with us. So that's a welcome, Professor Prakash, for a wonderful presentation today.
Thank you. Thank you for that introduction, kind introduction. And good evening, ladies and gentlemen. Can you hear me? Hello?
Yes.
Okay, that's great. It's a National Chemistry Week, and it's a very important event. Every year, our Southern California section does a very good job on this presentation. And also, this year, we are presenting this talk even in front of the American Institute of Aeronautics and Astronautics, along with the Southern California section of the American Chemical Society. So let me go back and share the screen now so I can show my presentation. Share. Can you guys see the screen?
Yes, I can see it.
Can you see it?
Thomas, can you see it?
Guys, can you see it?
Yeah, we can see it. We can see it.
Okay, all right.
Sure.
Today I'm going to tell you about a work that we have been doing at our institute for past 20-25 years. And the title of my talk is Long-Term Sustainability Through Carbon Dioxide Capture and Conversion, the so-called methanol economy. So why do we want to talk about methanol economy? Now, we have a big problem in the world. There is increasing world population, and there is increase in standard of living. And the increase in standard of living of the world population has come mainly by the excessive use of fossil fuels, such as petroleum oil, right? Gas, coal. These are finite sources. They're mostly made of carbon and hydrogen. They're called hydrocarbons. And once you combust it, they're non-renewable on the human time scale. Of course, burning fossil fuels, the carbon ends up in the atmosphere as carbon dioxide. And there is increase in carbon dioxide content in the atmosphere. Actually, currently this summer, it hovered around 415 parts per million. So it's a very tiny amount in the air if you think about it. That is 0.0415% of air is carbon dioxide. There is plenty of nitrogen in the air, oxygen in the air, 1% argon. But this small amount of carbon dioxide is a miracle molecule which takes care of all the living things on Earth through a process called photosynthesis. You've heard about that. Now, if you go back to in the world history, in the 17th century, the world population was around 545 million, but it kept on increasing. In 2000, we surpassed 6.2 billion. And today, in 2011, we have surpassed 7 billion. By 2050, the projection is the population of the world will be, if you talk to an optimist, he will say maybe 8 to 9 billion. A pessimist will say 11 billion. Are you still able to hear me?
Yes.
Okay, good. One of the things that the populations of the world are doing is they're using energy, to do all kinds of stuff. So if you compute all the energy that is used by humankind, at any one time, transportation, your TV on, computer on, power plants running, and for example, homes heated, air conditioned. We are currently using 180 petawatt hours or 18 terawatts continuously. That is equivalent to 18,000 power plants operating at 1 gigawatt. So this is the kind of energy that humankind is using continuously. If you compute all the energy that is being used all over the world. And this is supposed to go up by 21 terawatts by 2025, 30 terawatts by 2050. Now, majority of our energy, for example, came from burning so-called fossil fuels, coal, oil, and gas. And in fact, more than 80% of our energy is right now coming from fossil fuels. Coal is still used, not much in America. Actually, natural gas has replaced coal in America. But rest of the world, like China, India, and other places, coal is still a major driver for producing electricity. Oil is still used in large quantity. Natural gas usage is going up, quite a bit, especially in the United States. But if you look at the alternatives to fossil fuels, such as nuclear and hydro, they haven't changed. In fact, nuclear is just 4.8%, and hydro is only 2.4%, and combustibles and renewables and waste and all, it's all hovering around 10%, and other, which include solar, wind, geothermal, ocean energy, is 1.4 to 1.5%. So if you, with all the hoopla and talk going into alternative energies, especially in California, by 2035, we are going to go into all electric and stuff like that. We have a serious problem. So what are we going to do about this? Now, hydrocarbon sources is very important. If you look at the industrial revolution that happened in Great Britain in the 17th and 18th centuries, for example, 17th and 19th century, it was all by burning coal, generating steam. In 19th century, humankind used quite a bit of coal, and they discovered oil in the latter part of the 19th century. But in 20th century, coal, oil, and natural gas, fossil fuels became the main driver of production of energy, transportation fuels, and all that. And we got unprecedented prosperity after Second World War because we started burning so much of fossil fuels. In 21st century, this fossil fuel burning is still going on. But at the end of my lecture, you will understand that we have a problem, and we can only solve this problem by managing this carbon dioxide. And carbon dioxide is a molecule which contains carbon. And as a chemist, we can play with this molecule. In fact, this is a very important molecule in the in the survival of the mankind as we know it. Okay, as you will see in my lecture. Now, petroleum oil and other fossil fuel are also used not only for transportation to make gasoline, diesel, and things like that. It is also used to make so-called petrochemical products, chemical feedstocks. For example, you make plastics, you make agrochemicals, you make fertilizers. All these things are done through petroleum oil. So it's about 8 to 9% is used to make other products. And this is a very important for us. Without that, I think modern human cannot survive. So besides CO2, besides CO2 emissions, fossil fuels gave us unprecedented prosperity for humankind. That's what I would like to emphasize. Now, what has happened is burning all these fossil fuels over these years, every year we are using more and more fossil fuels. So it is creating more and more humankind caused CO2 emissions. People have computed this. There are computer models to do this. And in 2013, we released about 35 billion tons of carbon dioxide, excess carbon dioxide in the atmosphere. This is all anthropogenic, that is human caused CO2 emissions. And 2017, it was around 40 billion tons. So it's increasing. About half the CO2 emissions accumulate in the atmosphere. And and CO2 in the atmosphere, what it does is, can you hear me? Hello?
Yes.
Okay, good.
Yes, Prof. Prakash.
Yeah. The CO2, in the atmosphere, can absorb certain wavelengths of, sun's radiation, and then the heat is radiated back to Earth. So it causes global warming, and the global warming has increased what's called glacier ice melting, sea level rising, and climate change. I think, let me hide this. Yeah. Oh, what happened here? You can still see me, right? Okay.
Yes.
Yeah,
Okay, good.
You can
see. You can see. Okay. Sea level rising, and of course, we all talk about climate change. So there's warming of the atmosphere. Temperature is going up, and not only that's one of the major problem. CO2 also dissolves in oceans. Water is called ocean acidification. You're making more and more soda water, and the soda water is acidic. The pH is less than 7. It's around 6.2. So this destroys coral reefs, which is calcium carbonate, and which calcium carbonate, put carbonate into acid, you make more CO2. So it's an autocatalytic type reaction. So this is our major problem. Ocean acidification, destruction of coral reefs means all the sea life will be affected, because most of the sea life is originates from coral reef. So these are all the major problems of excessive CO2 in the atmosphere. Now the carbon dioxide conundrum, as I call it in the slide, it has also resulted in global temperature. You can see many things here. For example, you can see the blue line, is the temperature changes, and this solid line is the CO2 concentration, which is measured in Hawaiian island Mauna Loa, close to that volcano. And CO2 concentration is also given here. Okay, how the CO2 level is rising, and global average temperature has gone from 1.2 to 1.5 degrees. It's a pretty big change from the pre-industrial age. And currently, in August, this is measured on a daily basis. You can see this on Google. August 3rd, the reading was 413 ppm. In June, it was 418. It hovers around 415 parts per million, and it is slowly creeping up. Now, there are a lot of other greenhouse gas emissions, so that's happening. Carbon dioxide is the major culprit, about 76% contribution to global warming. Methane, which is natural gas, is 23 times more global warming than carbon dioxide. And methane emissions from, not only agriculture and animals, but also methane leakage and all, it's about 16%. Nitrogen oxides, which comes out of automobile emissions, heat engine emissions, this is about 6%. These are also pretty bad. And fluorinated gases, which are used as refrigerants, are also highly greenhouse warming. But if you look at it, the CO2 is our major problem. This is the carbon conundrum or carbon problem, we call it. Now, if you look at the global greenhouse gas emissions by economic sector, you can look here, industry contributes about 21%, transportation is 14%, and agriculture and forestry, this is all the, animal husbandry and all that is about 24%. Electricity heat production is 25%. So this is how, buildings, for example, heating and cooling of the building also contribute. And we humans are also, as individuals, are also emit CO2. In fact, we exhale CO2. Whatever carbon-based food we eat, eventually it's converted at a cellular level into CO2. And CO2 comes out, and you exhale it. And an average human being, an American, I could say, an average American over a 24-hour period exhales almost 1 kilogram of CO2. This is something to ponder for you guys. Now, Global temperature change, people talk about, you can't stick a thermometer. They're all models. People do models. If you compare to 1180 to, this 19-year period between 1180 and 1899 versus 2014 and 2018, 4 years, things have changed. In fact, in Arctic area, there is almost 6 degrees temperature change. Okay, it's amazing. Canada is about 2 degrees, and these are the, this was an article in Washington Post, September 11th last year. The fastest warming zones include Arctic, much of the Middle East, Europe, and Northern Asia, and key expanses of ocean. And this is what also changing our climate, our weather too, because when the ocean gets hot, there's a lot of heat in the ocean, the water evaporates, and you get a lot of rainfalls in certain areas and drought in some other areas. Okay, this is another problem of global warming. Now, what is the solution for this global warming? Engineers and scientists, they said, okay, if CO2, we have a lot of this CO2 where it's produced at a point source. For example, a coal burning power plant, the flue gases will have 10, 12% of CO2 in it. So why don't we separate the CO2, capture it, and put it underground in depleted oil fields, deep aquifers, deep oceans, depleted natural gas fields, and things like that. But this is a very expensive proposition. First of all, you need to separate it, and using sequestration facility. Then you have to inject it through various technologies. So this is a very expensive proposition, and carbon capture sequestration is a pretty difficult process to achieve economically. Okay, and so what is the alternative? Now, carbon dioxide, as a chemist, it's carbon and 2 oxygen. It's a symmetrical molecule. It has no dipole. But CO2 is a feedstock. You can do many things with it. For example, CO2 can be converted to polymers like polycarbonates, polyurethanes. CO2 is already converted with ammonia to make urea. It's a major fertilizer. Without urea, there won't be food production in the world. So CO2 contributes. CO2 and with ammonia you make urea. 150 to 200 million tons you make. It's used in food industry. You make carbonated beverages, Coca-Cola and Sprite and things like that. And it's also used to make decaffeinated coffee, which brings a lot of money for the a German institute, where liquid CO2 is used to separate caffeine from coffee. It's also used to make flavors and fragrances. It is used in greenhouses to grow tomatoes, green bell peppers, and cucumbers and things like that, spinach. So it's very important, CO2. It's also used for oil recovery, enhanced oil recovery, natural gas recovery, coal bed methane recovery. They pump it. This technology is already being practiced in Texas and other places. Methanol can also be used to make chemical feedstocks, like organic carbonates, inorganic carbamates, carboxylates, lactones, and things like that. And it's used in as a refrigeration, dry ice, supercritical CO2, even dry cleaning. People have used CO2. There are plants which run on liquid CO2. There's a fire extinguisher, a respiratory simulant, aerosol can propellant. There's a lot of injected into metal castings, things like that. More interestingly, CO2 can be converted to methanol if you have hydrogen. Methanol is a liquid. It's a fuel, feedstock. You can make formic acid, methane, dimethyl ether, dimethyl carbonate. So you can do a lot of stuff once you have captured CO2. Okay. Now, just to give you some numbers, ladies and gentlemen, if you look at the daily usage of fossil fuels, world is currently using close to 100 million barrels of oil a day. A barrel is 42 gallons or 160 liters. And 10 billion meter cube of natural gas, this is going up every year. And 16 million tons of coal was burnt about 2 years ago. It's a little bit decreasing right now. So all this activity is resulting in this CO2 release, and the greenhouse effect is becoming severe. Now, we all talked about biofuels. For example, nature uses carbon dioxide through photosynthesis to make all the flora and fauna, forests, and things like that. And if you use forest products or agricultural products like sugar or corn, you can make ethanol, which is a 2-carbon alcohol. And US converts 40% of its corn crop to make 13.9 billion gallons of ethanol a year. That's equivalent to 330 million barrels from corn. equivalent to 225 million barrels of oil. That's mostly 2.5 days supply for the world. So 40% of the American corn making ethanol is not a solution. In fact, there are people starving in the world. Corn is a food. So food security is more important to mankind than energy security. Brazil converts its very dear sugar crop, sugar cane, into ethanol too. So these are all very small. It's not going to supplant fossil fuels. It can only supplement alternatives to fossil fuels. Now biomass, nature does a wonderful job. Takes carbon dioxide and water with a green dye called chlorophyll. With sunlight, it is converted to so sugar, celluloses, and things like that. Okay, very nicely. This is called photosynthesis, and you can make biofuels like ethanol, butanol, vegetable oils. But this can only be a small percent of energy mix, because to practice photosynthesis, we need to worry about land mass, land availability, and use. We need a lot of water to grow crops. Irrigation becomes an issue. Then we need to feed growing population. How can you divert food into energy materials? It's not a good idea either. And of course, to grow food, you need for crops, you need fertilizers. And fertilizers comes from ammonia, which is made from fossil fuels. This hydrogen comes from methane reforming and things like that. I'll come back to this in a minute. So processing technologies, energy use, here to look at all that to make biofuels. Overall energy balance, life cycle analysis, you need to worry about when you're working biofuels. And also the efficiency of photosynthesis is pretty bad. To convert water, sunlight, and and also carbon dioxide in a photosynthesis in a rice plant, which takes probably 4 or 5 months to grow, is less than 1% overall efficiency. Okay, so nature is very specific, but nature is not very efficient. But we don't have to worry about this, because sun is the source of most energy on earth, past, present, and future. It is putting out 23,000 terawatt year per year of energy, a reliable nuclear fusion reactor, which comes every morning and then goes down every evening, on every corner of the earth, right? So the solar flux is amazing. It's almost, the estimate is 23,000 terawatt years. Okay, and and mankind is in 2009 used only 16. Now it may be 18 now. Look at all the other alternatives that you look at. Tides generate, which is also because of gravity. This is about 0.3 per year. Geothermal is this much. Hydro this much. Biomass is not that much at all, only 2 to 6 terawatt year. And the other types of technology too is not very much. But look at renewables. Wind is 70 to 120. And if you look at fossil fuels, which are finite, natural gas is 215. Sun is 23,000 per year. Okay, so it's coming every year, next 4.5 billion years. Petroleum is only 240. Uranium, which is for the nuclear energy, is 90 to 300. Coal is 900, but coal is very dirty. People are trying to get away from that. So if you understand this, Earth does not have an energy problem, ladies and gentlemen. It has energy storage and energy carrier problem. Okay. So what are the issues? Why do we have all these problems? Why not use more alternative energies and resources like hydropower, geothermal energy, wind energy, solar energy, biomass, ocean energy, or even nuclear energy, if you have the stomach for it? The problem with all this is these alternative energies, mainly the problem is cost, although the alternative energy costs are coming down. Fossil fuels are still the biggest bargain nature ever gave us, because you just dig a hole and you can get it. In Saudi Arabia, you make a hole and you can extract oil for just few dollars a barrel. The most promising solar and wind energies are intermittent and fluctuating. They produce mostly electricity, and battery technology has not advanced. Whatever Elon Musk says, still we have a problem with battery technology, because to make a battery, you need to produce you emit a lot of carbon dioxide. So if you look at the life cycle of making a battery and running a battery, it's not that clean if you think about it. Okay. Now, people talked about so-called hydrogen economy. Hydrogen is a light, one of the first elements, right? The periodic table. It burns cleanly. It makes water when it combines with oxygen. But it's not a primary energy carrier on Earth because it boils very low, minus 253 degrees Celsius. It's tied up in water and fossil fuels. It has to be liberated. You need energy for that. It's incompatible with 20% oxygen in the air. It's a love affair. It can explode under certain, ratios. The main disadvantage of liquid hydrogen is even liquid hydrogen has 1/3 volumetric energy density of gasoline. So the energy density per volume is terrible. Okay, 2 grams occupy 22.4 liters of volume at normal temperature and pressure. So you need high pressurization. So if you want to go beyond 5,000 psi with hydrogen in tanks, the tanks, become brittle. Anything which has carbon in the metal, it becomes brittle. So you need very expensive technology. For example, carbon fiber tanks to store hydrogen at 10,000 psi. Infrastructure is very expensive. It diffuses. It's a very tiny molecule. It can go through. If you have a hydrogen balloon, after some time, it's all diffused through the plastic, right? You see that. Same thing happens with helium too. It's highly flammable with a colorless flame. So hydrogen economy, although hydrogen is there everywhere on the, especially, in the outer planets and outer space, it is not a compatible or handleable fuel for us humans, mortals on Earth. So what is the solution? So about 25 years ago, Professor Ola and I and the local Hydrocarbon Institute, we came up with a concept called the methanol economy. So I'll tell you briefly what methanol economy is. And this was done with my mentor and colleague, Professor George Ola. And he passed away in 2017. And in 1994, he obtained Nobel Prize in Chemistry for superacid chemistry, which I contributed. In fact, I accompanied him to Stockholm with him to receive the prize. And he's one of the major proponents of the so-called methanol economy concept. What is methanol economy? Methanol is a simple molecule. It's a liquid alcohol, boils around 65 degrees Celsius. It was discovered by Dumas and Pelligot in France. They isolated from wood by heating wood chips. This methanol vapor comes out. It's called wood spirit or wood alcohol. And the beauty about methanol is it's a fantastic fuel for internal combustion engine. It's a high octane fuel, clean burning. It has 15.8 millijoules per liter of energy. It can be combined with 15% gasoline, and M85 is a fantastic fuel, 85% methanol, 15% for all IC engines. Methanol can be converted to a compound called dimethyl ether. It's a high cetane. That means it can replace all diesel fuels, and it's a gas replacing LNG and LPG. I'll come back to this in a minute. Methanol can be also converted to petrochemical products like olefins, gasoline, kerosene, aviation fuel, diesel, etc. And also methanol could be used to produce hydrogen on demand. It's a much more high volumetric energy density fluid than liquid hydrogen. And it can also be used in direct methanol fuel cell that was developed in our laboratories in the 90s in collaboration with NASA JPL. So I already said it's a wood alcohol, it's a liquid, excellent internal combustion engine turbine fuel, high octane number. Since 1950, it was used in race cars. And also methanol, it can be mixed with some gasoline. It's used in a flex fuel vehicle similar to E85, which is used in California, for example, and other places in America. So methanol can easily substitute ethanol, which is derived from corn. It has half the volumetric energy content of gasoline, but more efficient and cleaner burning. In equivalence, I can say if 15 gallons of methanol is equivalent to 10 gallons of gasoline in terms of power. Methanol can be blended into biodiesel. It's already done. Esterification, converted to dimethyl ether and dimethyl carbonate, which are also fuels in their own right. Methanol is an excellent hydrogen carrier because it is easily reformed to hydrogen at modest temperatures. Methanol is miscible in water, just is corrosive for aluminum, zinc, and magnesium. But modern vehicles are compatible to methanol. Almost all vehicles made since 1992 in America and rest of the world They're already flex fuel vehicles, so it's not a problem to have alcohol in the engine block. Only certain gaskets have to be changed. Methanol has low vapor pressure at low temperature, so you need to spike it with some gasoline. That's why they use 5% to almost 85%. Ingestion, you can't drink methanol like ethanol. Ethanol, we all enjoy sometimes, beer, wine, and things like that. But methanol can be poisonous. It can blind you. Ingestion can be lethal. But gasoline or diesel are equally toxic. How many times you go to a gas station or a diesel station, ask for a pint of gasoline or diesel to drink? You shouldn't do that. But having said that, methanol is found in beer. Methanol is found in orange juice in small amounts. Aspartame, the sugar substitute, has, when you react with stomach acid, it makes quite a bit of methanol. Small amounts of methanol is not toxic, but anything above 20 milliliters can be a problem. So you have to be careful. Spillage is very safe to environment. It's a plant growth promoter. It's already used to wastewater treatment plants for denitrification of water. It's a reducing agent for nitrates in water. So methanol in internal combustion engines, it's an octane number 100. So the air fuel mixture can be compressed to smaller volume, resulting in higher compression ratio. I know there are some aerospace engineers, they understand this very well. Methanol also has higher flame speed, gives you higher efficiency. And more importantly, methanol has high latent heat of vaporization. It's 3.7 times higher than gasoline. So it absorbs heat better, removes heat from the engines. It can be blended with gasoline in various ratios. It can also be blended with methanol, ethanol, and gasoline, called gem fuels. And Lotus, the race car company, has demonstrated that. And since methanol has high latent heat of vaporization, methanol burns cleaner. Very little NOx is produced with methanol engines. NOx is also a greenhouse warming toxic gas. Since methanol is a one carbon alcohol, you don't get any 2.5 micron particulate matter. Okay, this is one of the biggest pollutant from automobile emissions is NOx and particulate matter. So no particulate matter. And also methanol is safer than gasoline in fires because you can extinguish the methanol fires with water. With gasoline fires, you need foam. Methanol can be dispensed like a liquid, so we already have the infrastructure to dispense it. It's compatible with hybrid fuel electric systems. And China is one of the biggest adopters of methanol economy. In fact, many taxis run in China in methanol, buses run on methanol, there are dispensing stations in China. There are various road transport options. For example, M3 to M15, 3% methanol to 15% blended is done in UK, China, Australia. 20 to 30% is also, was done initially in China with different alcohols to boost the octane rating. But 51 to 100% is done mostly in China. China is big in this. And there's a car company called Geely, which is, they're the owners of Volvo. And they have shown that, in China, currently about 250,000 vehicles, this is an old data, but 250,000 vehicles are running on 100% methanol, mostly taxis. And, in 2016, 7 million tons of methanol was used, and sometimes used as such or blended with gasoline. And just to show you, these are the provinces in China where methanol is being used all the way, Shanxi, where there are a lot of coal, they make methanol. Even M100 vehicles are running. I know Shanghai is also have a lot of M100 vehicles. Israel has adopted some aspects of methanol economy because they found natural gas. They can make methanol out of natural gas. Iceland makes renewable methanol. I'll come back to this in a minute, a little bit later. Now, this is a Volvo-like car in China, Geely, which is 100% methanol car. Okay, and Israel has done a lot of demonstrations in this area. I was in Israel when I got my prize. It's very interesting that they have a small country. They don't have any petroleum oil, but they found some natural gas in the Mediterranean. So they're converting some of this methane into methanol. India is another country which is interested in adopting methanol economy because they don't have much petroleum oil. They have to import it. And also we have a lot of pollution like China. So substituting gasoline with methanol, our pollution problems will go away quite a bit. And this is a genset which can be easily, a diesel burning genset can be converted to methanol. Just you need to change some gaskets. It works beautifully. And also methanol can also be used in diesel-like engines. In fact, in diesel engines, it's called the compression stroke engines. You take fuel and air mixture, compress it. There is auto ignition. But methanol, you need to have a spark ignition. So people have made diesel engines, methanol engines, which resemble diesel engines. What's interesting is, look at this number, engine type. 9-liter diesel engine gives you only 1,300 pound-feet of torque. But the same 9-liter volume methanol engine give you 2,000 pound-feet of torque. So this is a game changer. You can make your engine smaller, and can make better tanks, better diesel trucks and things like that. Smaller, but you get much better performance. So you can have more room to carry methanol, which is half the energy density of diesel oil. And in fact, this super efficient spark ignition methanol engine, this work has been done by MIT, David Cohn. He has shown that you can increase the efficiency of a diesel engine, which is 30%. We can go all the way to 55% using methanol. Okay, so it's very, very game changer. And in China, I know this gentleman called Chunde Yao. He has taken a conventional diesel truck. It has for example, it has a diesel tank. Then you put a methanol tank. So you start your engine on a diesel cycle, the auto ignition cycle. Once the cycle is running, you start injecting methanol. Then automatically, you can get this combustion going. So your emissions and everything improves. $1,000 retrofit for a diesel truck, you can make a methanol truck. Marine fuels, there are 370 million tons of fuel, heavy fuel oil and middle distillates are used, and they are very polluting. Ships use the worst fuel because they are in high seas. Nobody is monitoring them. And they produce a lot of sulfur oxides, NOx, particulate emissions. And so this is a big issue. And especially in the Baltic area, there are a lot of shipping activity between the Scandinavian countries and the European countries. And they made a rule recently, it's called the Emission Control Area, that they monitor all these pollutants. So a second largest shipping company in Sweden decided to convert their shipping, huge ships, into burning methanol instead of diesel. Existing diesel engines were converted to methanol engines by retrofitting. So this can be done. And even Methanex is running their, it's a big methanol trading company. Some of their ships run on methanol right now. In fact, before the engines and after, they just had to have some injectors and things like that. You can convert them to methanol engines, and they're much cleaner burning than conventional diesel. Methanol can also be dehydrated to dimethyl ether. It's a gas boiling at minus 24.8 degrees. It's almost like liquefied petroleum gas, like propane. Low melting point. It's an excellent diesel fuel substitute with a cetane number of 55 to 60. Regular diesel is 45 to 55. Very clean burning, extremely low NOx, SOx, and PM. There is no sulfur here, no SOx. It's already used in spray dispensers. It's non-toxic, safe, and does not form peroxides. It's very interesting. It's substitute for LNG and LPG. Cook with it. Easy to produce, ship, and dispense. It also does not form any soot. Can you hear me? Hello?
Yes, Prof. Prakash, we can.
Yes,
Okay.
you can hear.
Okay. And also it is used in sootless flame for glass blowing. And there are, for DME trucks are operating, in Japan, Denmark. Volvo is one of the big operators of DME technologies in the world. Now, it can also be, methanol could also be used to produce hydrogen, to run a hydrogen fuel cell. You all know about fuel cells, where hydrogen oxygen fuel cell, very clean. It's basically a proton exchange membrane type fuel cells where hydrogen is oxidized at the anode and oxygen is reduced to cathode. So you produce water, and the chemical energy is directly converted to electrical energy through two redox processes. H2 is oxidized to protons and electrons at a certain potential. At cathode, oxygen is reduced with protons and electrons to water at this potential. If everything works, you connect a wire, you get 1.23 volt DC. And depending upon how much hydrogen, you get different current density. In fact, you can get 1 volt at 1 watt per square meter kind of a situation. You can do that, okay? So this is already has been achieved. Square centimeter has been achieved already, especially Toyota Mirai and all have that kind of capability. So you can use methanol and water and reform it to hydrogen, and hydrogen can be fed to your fuel cell. In fact, people have looked at it. And so you don't have to carry high pressure cryogenic hydrogen, in your vehicle. So methanol is a nice liquid. It is twice the energy density of liquid hydrogen. And in fact, you can onboard reform too. There are technologies coming. You take methanol and water, catalytic reforming. In fact, this fuel cells are available with a reformer attached, 5 kilowatt type systems. And in fact, this company, Blue World Technologies, is going to make 50,000 15 kilowatt stacks, where you put methanol water mixture is the fuel you take, and you produce hydrogen on board. A vehicle like this running on 150 kilometer range with a hydrogen fuel cell can now run to 800 kilometers or even 1,000 kilometers. Okay, so people are thinking so-called range extenders. And there are, for example, Fiat cars have been made with these kind of technologies. There is this type of things are also available. Which is Sur Energy reformer units, where EcoMotion, has developed a lot of technologies in this area. Falcon Motors in China has these vehicles which have basically you put methanol. It's a fuel cell vehicle, very clean. Emissions are clean, very nicely done. Now, when you take methanol and water, this is some chemistry for you. You can reform it and get CO2 and hydrogen. And hydrogen can be, this is a 12.1% hydrogen carrier. That's what methanol and water mixture is. It's amazing. In fact, there are a lot of chemistry that has gone into this. People have studied using different heterogeneous and homogeneous catalysis. And our group has been very active in this area. And of course, when you reform with water, you produce CO2, it's a greenhouse gas. So our group in USC developed another process. Instead of using water, we use amines to reform methanol, and we get urea and 3 moles of hydrogen. So it's a 6.68% hydrogen storage. Idea. DOE was looking something better than 5%, and we already got this. And the interesting aspect of it is you get the hydrogen, burn it in a fuel cell, then the cyclic urea can be converted back to methanol and primary diamine using hydrogen and a catalyst. So it's a CO2-free hydrogen storage approach, that was developed in our laboratory. And this paper was published in Journal of American Chemical Society in 2017, which got a lot of attention from, press and all that. Methanol could also be used in direct oxidation methanol fuel cell, where methanol and water can be directly reacted on a platinum ruthenium anode. I've given it here. And this happens at very low potential. And the oxygen reduction you can do at 1.22 volts. And if you look at the difference, this also gives you 1.2 volts. In fact, we developed this with a DARPA-E project with NASA, JPL, and Caltech and USC. And we have a huge patent portfolio in this area. Now, the methanol fuel cells are very good, very easy to operate. They operate at room temperature. Maybe at the end of my talk, I'll show you with a demo. And the direct methanol fuel cell has advantages. It has 5 kilowatt hours per liter of energy, theoretical density, twice as hydrogen. When it burns, it works. It only makes H2O and CO2 are the only byproducts. You don't have to reform it. You can directly feed liquid methanol. It starts at low temperature. So it's a lot of military applications are already happening. Liquid feed of reactants means, heat removal, thermal management, polymer dry out won't happen. And we have licensed this technology to a company called Smart Fuel Cells in Germany. They're already marketing, 70 watt hours to now 5 kilowatt hours of portable devices based on this technology. There are vehicles running on methanol fuel cells. Methanol can also be used in solid oxide fuel cells, at high temperature. And Wärtsilä has done it in Europe. In fact, this they have built. You can buy this in the commercially 20 kilowatt methanol solid oxide fuel cell. It's a device like this. You just put methanol, you get electricity. Methanol is also used in cooking, very clean. China uses 3 million metric tons of methanol for cooking. with potential 8 million metric tons of demand, okay? Because it's very clean burning and it's much better than kerosene, because kerosene makes this dark smoke or soot. And in fact, this is very popular in China, especially in restaurants, to cook with methanol. And India is doing this in a state of Assam. They already made clean cook stoves. It's made by a private non-profit organization. They're giving, and you get buy methanol in canisters. It's very clean, and the food apparently tastes much better cooked with methanol than with kerosene. Methanol is also used as a boiler fuel to make steam. In China, believe it or not, there are 1,000 boiler units in industries which are converted to methanol, because methanol is not only clean. In China, methanol is also quite cheap. It's made in large quantity. So methanol can also be used as a fuel. I just mentioned all now. It is also a chemical feedstock. You can also produce electricity in turbines. In fact, methanol also could be used as a jet fuel. I'll come back to this in a minute. If anybody's later, if anybody's interested, we can talk about it. And in Israel, there's a 50 megawatt power plant which runs on methanol, which used to burn oil, because it's in a place called Eilat. Eilat, tourists go there, so they wanted to keep the atmosphere clean, so they changed it to methanol. Cooking fuel has a lot of potential. There's a non-profit called Gaia, Project Gaia, and they're giving these clean cook stoves to use methanol worldwide. Of course, methanol is used to make chemicals like formaldehyde, methyl tetrabuthyl ether, acetaldehyde, acetic acid, vinegar, polyethylene, polypropylene, other chemicals. Methanol also can be fed to lower level organisms like bacteria. They make single cell proteins, which is used as a feed for animals. In fact, ICI company in UK produced 100,000 tons of animal feed using methanol as the carbon source. So methanol, you could do all this interesting stuff. And methanol, a one carbon solution for a one carbon problem. You can do methanol to olefins, acetic acid, gasoline. All these things are done. In 2015, 70 million tons of methanol was consumed. Today, there is about 90 to 100 million tons of methanol capacity in the world. And I'll come back to how this methanol is currently made, and we can talk how we can make it differently. Now, methanol could also be converted to ethylene and propylene, two feedstocks to make polymers. And this technology is already commercial. This is called the MTO process, which we worked on in the 1980s at the University of Southern California. Once you have ethylene, propylene, ladies and gentlemen, you can make all the products of petroleum oil, like pharmaceuticals, agrochemicals, fuels, gasoline, diesel, even kerosene, the aviation fuel, can be made very easily through methanol as a feedstock. China, believe it or not, is making almost close to 30 million tons of ethylene, propylene through methanol. It's methylene, propylene. Methanol, China makes around $120 a ton. And what is and it can take that methanol and convert to ethylene. And the world price for ethylene is $1,200 a ton. Propylene is $1,400 a ton. So they're doing a lot of value additions because they don't have to import ethylene and propylene from the world market. So where do we get this methanol? Industrially, it is produced from syngas, from coal or natural gas. I'll come back to this, what syngas is. You can do direct methane oxidation. You can do biomass gasification. But if you can do also what's called carbon dioxide reduction, capture carbon dioxide, reduce it, you can make methanol. Naturally, it is made from wood. It's called wood alcohol, but you can't make much out of wood. There's not enough wood to go around. But methanol is also found in outer space in large quantity. Nobody knows the origins of it. With Thomas Matthew, who is in the audience, with George Ola, we speculated how this methanol might have been formed in all these galactic clouds, close to nascent stars and things like that. In America, there is a lot of what is called shale gas, we found in America. And there was a report in 2012 by Moniz, who was the DOE secretary. It's called The Future of Natural Gas, an interdisciplinary MIT study. The potential for natural gas to reduce oil dependence could be increased by conversion to room temperature liquid fuel that can be stored at atmospheric pressure. Of these fuels, methanol is the only one that has been produced for a long period at large industrial scale. Methanol has the lowest cost and lowest greenhouse gas emissions, but requires some infrastructure modification, but faces substantial acceptance challenges. So this is the problem, because somehow people believe, everybody thinks, oh, methanol is not good because it is toxic. Actually, gasoline and diesel are more toxic. Okay, you can't drink it. So methanol also, you're not supposed to drink it. So natural gas derived gasoline and diesel have the advantage of, so we can convert even methanol to gasoline and diesel if you want, but it's an extra step. Okay, that's the problem. So methanol is made from CO and hydrogen. It's called carbon monoxide and 2 moles of hydrogen. You make methanol. It's an exothermic process. You can take CO2 and 3 moles of hydrogen. You make methanol and water. And carbon monoxide and water can also go to hydrogen and CO2. It's called water gas shift type reaction. And syngas can be produced from any source of carbon: natural gas, petroleum, coal, biomass, CO2, etc. Okay? So initially, the world used to take methane, natural gas, water. At high temperature, they reformed to CO and 3 moles of hydrogen. It's a very endothermic process. And excess hydrogen is used to make ammonia. So this is practiced in 1930s in a very big fashion. And once you have hydrogen and CO, you can make methanol, or you can do oxidation of methane to make CO and 2H2. And CO can be further oxidized, hydrogen can be oxidized, okay? Or you can reform methane with CO2 to make 2 CO and 2 hydrogen. But you need, I already told you, this ratio, CO to 2 hydrogen to make methanol. This gives you excess hydrogen, this gives you less hydrogen, okay? So what we did was we came up with an idea at my institute many years ago. We took a steam reforming equation, dry reforming equation, we just combined it. So 2 times the steam reforming, 1 time dry reforming, combine the ratios, 3 methane, 2 water, CO2. We make 4 CO and 8 H2, we can make 4 moles of methanol. Nicely balanced. And we developed a process, a commercial process, I could call it, although nobody has licensed it yet. We can do this to get right ratio. We have a lot of patents in this area. So bi-reforming of methane will give you very efficiently methanol. And we can also do what is called oxidative bi-reforming, where you can take the exothermicity of this oxidation and combine with the endothermicity of this bi-reforming, and we can even make it, cost effective. So we are working on this area too. Methanol can also be made from coal, and China and India are considering this. In fact, China makes most of it methanol, almost 55 million tons a year, through coal reforming, using water and coal, making syngas and converting it to methanol. But this has a very high CO2 footprint. But the problem with China is methanol is a much cleaner burning fuel compared to gasoline or diesel. That's why they're using it, because they want to keep their cities clean. Methanol can also be used from biomass, non-edible biomass. You can gasify it to syngas and make methanol. In fact, there are already processes going on, but the scale is not very high. You can use wood waste, agricultural crops, municipal waste, animal waste, aquatic plants, algae, etc. Now, you can also take this biomass like lignocellulose. You can do pyrolysis. You get condensate, char. It's called the black oil, and it can be heated with oxygen at high temperature. You get syngas. You can make methanol and other liquids. In fact, there's a company that used to be, Chemrec. They took lignocellulose from paper industry in Sweden, made black liquor, syngas, made directly dimethyl ether, and Volvo used to run a lot of trucks on dimethyl ether. Biomethanol can be made from glycerol, which comes out of biodiesel industry. Glycerol can be gasified, and in the Netherlands, they were thinking of a 200,000 kiloton capacity. They were planning making methanol from glycerol. Now, we can make methanol from carbon dioxide. Carbon dioxide is a very stable molecule, linear molecule, difficult to work with. It's very low concentration in the atmosphere, around 0.0415%. I said, it's 415 ppm right now, and many places CO2 is released: geothermal vents, fermentation processes, natural gas wells, cement plants, fossil fuel burning power plants, aluminum plants, and air itself has CO2. You can use technologies called absorption, using CO2 is an acidic gas. Chemically, you can treat with the base. You can dissolve it in solvents. There are processes. You can use solid adsorbents, you can use cryogenics, membranes, or you can give it to algae and microbial systems so they can grow in CO2 atmosphere. But we decided early on the best way to capture CO2 will be from air, because all the CO2 that is released will eventually be equilibrated with air at this 415 ppm concentration. Collecting CO2 from a tailpipe of a car will be difficult, or an airplane will be difficult, or from a train will be difficult, or from animals will be difficult. So our whole idea is, can we develop a technology to capture CO2 out of air? This is where we used our chemistry principles. Our institute is very active in this area. We can capture CO2 directly from air using adsorbents that were developed at USC. And we had projects supported for this kind of stuff from DOE and ARPA-E. Now we developed based on silica some materials, and silica itself, is a lot of pores in it. And we looked at fumed silica, large volume mesopores and macropores. And we decided to put some amines, like polyethylene amines. These are all nitrogen bases. I already said CO2 is an acid. So we said, why can't we do an acid-base type reaction using amines and capture CO2 out of air? So we developed this polyethylene amine supported silica. They look like this, night flowing, powders. And we have a lot of chemistry we have developed over the years in this area. And once we have the CO2 reacts with the secondary amine to form the carbamate, and the carbamate, it's basically a negative and positive, is a zwitterion. That means 2 nitrogens capture 1 CO2. But if you have water around, you form ammonium carbonate, bicarbonate, 1 CO2 per amine. This is very effective. So we can, under humid conditions, which is usually there is anywhere in the world, there is, humidity is very high. Even in Saudi Arabia, this desert, the humidity is around few percent. So there's always water around. So humid capture is much more lucrative for CO2 capture. So once we capture it, we can thermally heat it and liberate it. There are various techniques, and we have adopted simple temperature swing desorption technique, adsorption technique. In fact, we developed some materials on PEI, on fumed silica. We had our first paper in 2011. We showed that this can absorb CO2 from air pretty well over a period of time, and then also it dissolves pretty well. And initially we showed that CO2 air, you get CO2 free air, we can capture 75 milligrams per gram of the adsorbent, which is pretty neat. Nobody had done that. And we can routinely do now 100 milligrams per gram reversibly. We have shown that it works very well. I'll go a little bit faster because of the time. And we can show that this adsorption desorption, we show 157 milligrams of CO2 per gram. It's very clean. We have done thousands of cycles, okay, using our materials, adsorption desorption. In fact, this technology was licensed to a company called Enverit, and they use our material in filters like this, and these filters are put in the air handling equipment in their buildings. For example, there are 80 buildings in America and rest of the world where our material is produced in ton quantities, and they're used to collect CO2 within the building. See, what happens is when people start working in high-rise buildings, 8,000, 10,000 people, everybody exhaling CO2, the CO2 level in the building goes up. That means the mental faculties come down. And so they have to bring outside air, the huge air handlers, which is heating and cooling air and bringing inside. So there's a lot of energy cost associated with air exchange from outside to inside. With our technology, we can capture CO2 within the building. That way our air handlers could be 30% smaller. You save 30% energy costs. So this company has been very effective in using our chemistry to develop a commercial technology for indoor air capture. Now once you capture CO2, ladies and gentlemen, you can take hydrogen and CO2 make methanol, and methanol could be used for all kinds of purposes. So it goes back to air. From air we capture CO2 and we can make methanol. In fact, we have done a lot of work in this space, and most recently we have been working on direct air capture. So we take air, bubble it through these polyamine solutions, then in situ we hydrogenate using different catalysts, and your amine is liberated to capture CO2 subsequently. And our first paper published in 2016 got tremendous attention in the press. 300 websites all over the world carried this story that we were able to make fuel out of thin air. That was this story. We have used less expensive catalysts based on cobalt and manganese, and Beller has done cobalt, we have done manganese. And we also have done recycling catalysts in a biphasic system. We have been able to do that. These are all published. I don't want to go too much into it. And more recently in February, we showed that we can capture CO2 using alkali media, like sodium potassium hydroxide media in ethylene glycol, and we can make methanol, and then we can grab CO2 again and again. Integrated CO2 capture and conversion system, a carbon neutral cycle. And this is a tandem hydrogen capture CO2 in ethylene glycol. We have some, we can get 90 to 100% conversions, to methanol. And we are ready for the next system. And this was published in 2020, February. The amine-free system for integrated CO2 capture and conversion to methanol has been developed. We used KOH, where KOH is regenerated after methanol synthesis, so you can use it for subsequent capture. And we have some side reactions which we are trying to avoid. And this got even a nice story in CND News, Chemical Engineering News. One part process converts CO2 capture from air into methanol. Now, we also have taken flue gases, which comes out of a coal burning power plant using tertiary amine capture. This paper got published a few days back. And we can do that too. So, we are working in this space. Now, what I haven't told you is, where do you get the hydrogen? You can electrochemically directly reduce CO2. In fact, we also work in this space. CO2 with electron make the radical anion. 2 proton, 2 electron, you make carbon monoxide or formic acid. You can make formaldehyde, methanol, 6 electron reduction. 8 electron reduction gives you methane. All this has been done. People are looking into it. So the sources of carbon dioxide you can get from anywhere. Hydrogen and CO2, you could do this already. But electrochemically, we have shown that CO2 and water with electrons and electrode catalysts, we can make syngas to make methanol. Electricity needed for hydrogen or for the reduction can come from any renewable, wind, solar, etc. Okay? We have a patent in this space too. Water electrolysis is a very well-known process. You can electrolyze water. The theoretical efficiency in practice, it used to be 39.4 kilowatt hours per kilogram. Okay, the theoretical efficiency. Currently, it's about 50 kilowatt hours per kilogram of hydrogen. Okay, at 4 cents kilowatt hour, if you pay for alternative energy, it costs about $2.6 a kilo hydrogen. The main driver for hydrogen production is the cost of electricity. So CO2 and hydrogen can be converted to methanol. At 4 cents a kilowatt hour, you can make methanol at $1.8 per gallon. Okay, so this is so if your solar power or wind power, sometimes wind energy, they give it away at night because they don't know what to do with it. So you can make hydrogen and convert it to methanol. In fact, we are practicing this in a plant in Iceland, in Reykjavik, where we take cheap geothermal electricity and hydroelectric power, make hydrogen, and CO2 comes out of geothermal steam, which is quite pure actually. And we are making about 12 tons of methanol a day. And this methanol plant was named after my late colleague Giorgiola CO2 to renewable methanol plant. And if you if you use this methanol, which is called volcanol, you get 90% reduction in CO2 emissions compared to gasoline. So this is the kind of stuff as chemists we should do. See, methanol as a fuel, I don't have to change my infrastructure. I can keep the existing infrastructure, existing pipelines, existing cars will happily run. And 1968 Toyota would run happily on methanol very cleanly. Okay, so 40 kilowatt hours of electricity energy is needed to produce a gallon of methanol. So this is something you guys should take home the message. So if the electricity is 1 cent or half a cent, you can make methanol very cheaply. So this ubiquitous methanol is a fantastic fuel and chemical feedstock. It can be made from natural gas. Currently, you can do it. You can make from coal. China does it. You can make it from biomass, biogas, and things like that. but ultimately it can be made from CO2. And of course, the methanol can be converted to dimethyl ether. So CO2 is a one carbon problem. We all talk about greenhouse problem. And methanol could be a one carbon solution. It's called the KISS principle. Keep it simple, stupid. Methanol could be a bridge fuel in the short term and renewable carbon neutral fuel in the long term. So we have for the one carbon problem, we have a one carbon solution, ladies and gentlemen. So we can use CO2 from the air. So it's called the anthropogenic carbon cycle, mimicking nature's photosynthetic cycle. We can make methanol currently from fossil fuels, which is not good. We don't want to do that. But once we run out of fossil fuel, we can take atmospheric CO2, grab it, use any alternative energy, solar, wind, hydro, geothermal, atomic, if you have stomach for it, make methanol. Not only use it as a fuel, but you can make all the carbon-based products. Remember, all living things on Earth is made of carbon. We cannot divest from carbon. Okay, if carbon is a problem, carbon has to be the solution. So this we call the methanol economy, sustainable recycling of atmospheric CO2 to fuels and materials. And we wrote a very influential book with George Olah. This was the third edition. He couldn't see it. He was already dead. But with my colleague Gopart, we did this. And this also translated to Chinese and other languages. It's already mentioned before. And methanol fueled cars could drive us toward an emission-less future. This was covered in IEEE Spectrum magazine in June 2018. And I was interviewed, and methanol gives us a way to store not just kilowatt or megawatt hours of power, but gigawatt hours, Prakash says. It could be a game changer. So methanol is just a storage medium. And methanol not only is a fuel, it's also a feedstock to make all important products like plastics, agrochemicals, fertilizers, which we currently make from fossil fuels. If you use renewable methanol to do that, CO2 is recycled from air, you have tiger by the tail. Now, why is America is not adopting? Oil companies don't like this idea, at least for next 15, 20 years. And of course, America has a lot of fossil fuels still available. And as Winston Churchill said, Americans will do the right thing in the end after exhausting all other alternatives. And also this famous philosopher, Arthur Schopenhauer, said, all truth passes through three stages. First, it is ridiculed. So our methanol economy is not ridiculed anymore, but there are people who are violently opposing it. Then once it's adopted, third, it's accepted as being self-evident. So we are waiting for this, in the future. So with this, I would like to thank my colleagues, who made this happen, especially Professor Olah, who was my mentor and colleague. We spent more than 40 years together, which I thoroughly enjoyed. I came to his group in 1974 as a PhD student from India, a 20-year-old kid, and we did a lot of stuff together. And all my other colleagues who have contributed, their names are given here. The support of our work at USC came from the local Hydrocarbon Institute, National Science Foundation, Department of Energy, DARPA, ARPA-E, a company which we founded, Stack Energy, and the Olah Nobel Laureate Chair Fund. And this is our group about a few years ago in sunny Southern California. And some of them are not here. And my colleague Rasul, who was a fantastic, chemist, a theoretician who passed away, last year. We miss him dearly. And in fact, it was already mentioned that in 2013, we were recognized by $1 million prize by the Israelis for our methanol economy concept. And that year, I had a tax problem. With that, I think I will conclude my talk. And let's see, I need to share comment. Stop sharing. Can you see me now? Yeah. All right. Thank you. Can you hear me?
Thank you, Professor Prakash.
Yeah, Professor, I thought you would like to do a demo.
Demo, okay. And I told you about the methanol fuel cell. And methanol fuel cell, has a this is the heart of a methanol fuel cell called a membrane electrode assembly. You have a polymeric membrane, and you have an anode and a cathode. It's like a battery. A fuel cell is like a battery. And what I want to show you is we developed this in the 1990s with a project from DARPA. And I put this membrane electrode assembly in this little bit toy where the anode, the cathode has holes. I don't know whether you can see it. And it can grab oxygen out of air. And the other side is a reservoir where I can put methanol and water. So what I'm going to do is I'm going to add the methanol and water to this little toy and see what happens to this small propeller. Okay, I'm going to hold it here. And can you see it? See, I'm going to add some methanol and water and see what happens to this little toy, you know. It starts running. It's making electricity and running this motor. So methanol and air is reacting in this little gizmo, making CO2 and water, and the chemical energy is being converted directly into electrical energy at 45% efficiency at room temperature. And this has been commercialized. In fact, all DoD, different defense forces have portable methanol fuel cells for their communication gear in Afghanistan theater and other places. Germany, India, US, they all use this technology. So this is my demo, okay? I'll just leave it here. I'll be happy to answer questions.
Yes, everyone. So this is a Q&A. So any question can. You're welcome to unmute yourself and speak out.
Okay, so it looks like everybody's going to buy a methanol car tomorrow, but you have to go to China to do that.
I see. So just a quick question, and how, I think you probably mentioned it, but how does it compare to the hydrogen?
Because cell? No, actually this methanol fuel cell is, it uses platinum ruthenium. The loading, metal loading is higher than hydrogen fuel cell, but we are doing some active research to bring down the, metal loading, the catalyst loading. And we are also trying to make other metal catalysts, but we have not been successful. We have been working for almost 20 years now in a stealth project to come up with alternative catalysts. The first catalyst we found, platinum ruthenium, is still the best catalyst for methanol fuel cell. But the beauty of methanol fuel cells is, the fuel cell is the catalyst can be recovered. It's like gold, jewelry. Gold is always recovered. So platinum can be recovered. So you buy a methanol fuel cell today and work for 5 years, and the company will take it back because the platinum prices would have gone up. So, it's a noble metal, right? So.
Yeah, it's very. This is very impressive, very inspiring. People know how important chemistry, can benefit the.
Sure.
The
one point I wanted to tell people was, methanol is an aviation fuel too. People are looking into it because the people are talking about electric planes. Because electric planes can land, on a street, and with all these electric motors, almost like a helicopter, it can land and then go like a regular plane and all that. So methanol could be an interesting fuel. And also remember, methanol is already oxygenated. So it's a fantastic fuel for jet engines. Because when you go 30,000 feet in the air, you have to grab so much of air to oxidize kerosene, the aviation fuel. And they told me if the oxygen is already built in the fuel, methanol could be a comparable fuel to, for example, aviation diesel or kerosene. So this is something people are looking into even in aviation industry, like places like, Boeing and other places. We had some people came and talked to us about it.
Yeah, certainly this aviation fuel is very important. Actually, we always have this electric hybrid AIAA, electric hybrid aircraft event. Maybe next time you can join us.
Sure.
That's shared, and this is absolutely amazing. And of course, we also have the news that in addition to Boeing, those companies, we have the news that you are right that the fuel very useful for aerospace. For example, a company called Reaction Engines in UK, they are actually using testing using ammonia. as
Sure.
a jet
See,
engine
but
gas.
see, ammonia, the problem is ammonia is much more toxic, it'll kill you. And it's ammonia also, you have to put it under pressure to make it a liquid. So ammonia, although talk about it, of course, when you burn ammonia, you got nitrogen, so there is no carbon footprint. But what I'm telling you as chemist, you and I are made of carbon. So it's very difficult to divest from carbon. We built all this infrastructure based on carbon. So coming up with new infrastructure is very expensive. So with methanol, you can keep existing infrastructure without that much change. And you can do all these things by this recycling. Yeah.
Yeah, that company, Reaction Engine UK, actually they are planning for 2050, not for immediate use.
I know. So this is what I'm trying to tell you. So there are a lot of technologies, but you need to think about. And I think we have solutions. And it's America, unfortunately, suffers from a disease. They ask me, how come America has not adopted this? America suffers from a disease called affluenza. We are too affluent for our own good. That's our problem. We used to be very innovative, but not anymore. Other countries are doing it because they need to.
Yeah, and the good thing you mentioned, this the methanol using the existing facility infrastructure. I think that's beauty, really beauty. It's really amazing, and the chemistry can be so beautiful. Make things so well. That's really amazing.
Thank you.
So, yeah, it's really beautiful, amazing.
And I will send you my presentation as a PDF file. If you want to, give it to people, please go ahead.
Yeah, that would be wonderful.
Yeah.
People will love it and know more about this fantastic, chemistry application invention. That's will let more people know about your research and great accomplishment.
Thank you.
Yeah, great pleasure, honor. So, any more questions? This is a great opportunity. All right. So if no more questions, let's thank Professor Prakash, and we look for further opportunity to have you speak with us or articles.
Sure. Thank you.
Us.
Okay.
Yeah.
Take
I
care,
will
guys.
stay in touch. Yeah.
Okay.
Thank you so much.
Okay. Bye.
Thank you.
Bye.
Thank you, Dr. Prakash.
Thank you, Professor
Sure. Take care. Bye.